Hello. All right, all right, all right, all right, all right. 5 minutes for people to join in. Hello, everyone. Oh, hello, hello, hello. Can you hear me? Ndiyavakala. Reply yes if you can hear me. Anyone? All right. Clean, 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 clean. Okay, 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 okay. So, I'm gonna start with question 9 here, which is on your oxidation reduction. So I'll just kind of go through it as a form of revision so that you understand what is it that we are all about when we are doing EL or redox reaction. So just a small Yana revision. So redox comes from the joint weight. So redox is coming from red, which means reduction. So this is reduction. And then oxidation here. Ox is oxidation. And then now we do know our definition walapho. So they will ask you to define this according to two methods. It can be according to electron transfer, right? Which according to electron transfer, this is how you should define what a reduction is. So we say reduction is the gain of electrons. Whereas oxidation is what? Oxidation is the loss of electrons. Is the loss of electrons. Then a simple way to remember that is by using oil rig. So oil rig ethini, yiyo lesitshela ukuthi oxidation is loss, reduction is gain, right? So from here you can remember that oxidation is loss, right? Loss of what? Electrons. Remember, redox is simply an electron transfer reaction. And then here, Rick tells us that reduction is gain. So it's a simple way to remember those. Now, it can be according to electron transfer. Sometimes Bangati define what is reduction or oxidation in terms of what? In terms of oxidation number. In terms of oxidation number. If they say in terms of oxidation number, then this is how you should define reduction. Reduction is a decrease in oxidation number. A decrease in oxidation number. Right? And then oxidation is what? We say oxidation is an increase in oxidation number, right? So ibanjalo. So reduction is a decrease in oxidation number. Oxidation is an increase in oxidation number. So if you want to remember it, think of it as in terms of a number line, and then you say, let's say you have 0 here, which is neutral. So the more you go to the left-hand side, the more you go to that side, it's what we know as oxidation. So if you are moving from a bigger number to a smaller number, then it's oxidation. But if you are moving from a smaller number to a bigger number there, and then we say that is a loss of, it's a what? It's a decrease in oxidation number. So oxidation, okay. Right. It's the other way around. Yeah, right, I'm error. So oxidation is when you move to that side. This is oxidation. It's a gain. It's an increase in oxidation number. And then reduction is when you move from the positives to the negatives. So from positives all the way to the negatives, it's reduction. From the negatives all the way to the positives, then it's oxidation, right? So oxidation is an increase in oxidation number, while reduction is a decrease in oxidation number. So very important for you to note that. Now, obviously, from there, you must also know ukuthi sinezinto ezifana nabo reducing agent and oxidizing agent. Now, it might be a little bit confusing, so I want you to understand this. When we are talking about a reducing agent, remember when something is an agent, it is responsible for making the other one to go through that thing, but you're not able to undergo the opposite process. So this is a reducing agent. A reducing agent undergoes what? Undergoes oxidation. So why do they call it a reducing agent? Because it reduces the other substance, right? It reduces the other substance, but in turn, it oxidizes, right? So undergoes oxidation, so meaning it does what? It oxidizes. And in terms of the what you call the oxidation number, how will you see that it's a reducing agent? A reducing agent will increase in oxidation number. So this one you will notice by an increase in oxidation number. An example could be Ag, which changes to Ag plus. So from an oxidation number of 0 to an oxidation number of positive 1, that's an increase in oxidation number, right? So that's what we refer to as a reducing agent, right? And then from there on, we have what we call an oxidizing agent. What is an oxidizing agent? It would have to be the opposite of what a reducing agent is. So oxidizing agent undergoes what? Undergoes reduction, right? And then this one, it means that it reduces. And then how do we see that? There will be a decrease in what? In oxidation number. So a decrease in oxidation number is indicating that there is an increase in what? There is a gain of electrons, right? So an example could be, Cl2, which changes to Cl minus from an oxidation number of 0 to an oxidation number of -1, right? So that's a decrease in what? In oxidation number. So from 0 to -1. Kusho ukuthi sisuke siyaphi? On the left-hand side of the number line. So you just look at the values. Are we going more to the positive side? Are we going more to the right-hand side? That's oxidation. Are we going more to the left-hand side of the number line? That's reduction. But you must understand this. If it's an oxidizing agent, it undergoes reduction. If it's a reducing agent, it undergoes oxidation. Okay, so quickly note down my notes lapho. quickly note down just a few minutes. You can even screenshot it, just to make things faster. And while I'm explaining something else, you can be writing down in your book. Be done. Okay. Let me move. Then common things that you might face is this, and yet we are given a question here, and then we are given this reaction here, copper solid plus 2Ag plus, and then in aqueous to give us Cu2 plus aqueous and 2Ag. And then here we are told 9.1.1 define reduction in terms of what? Electron transfer, right? In terms of electron transfer. They say in terms of electron transfer, that means this is routine again, manje. This is where we define and say reduction is the gain of electrons. So if they say according to electron transfer, this is the definition. Awubali abo reduction is the decrease in oxidation number. That's in terms of oxidation number. So according to electron transfer, this is how you should write your definition. Reduction is the gain of electrons. Then 2 marks. What type of reaction does copper Cu undergo in this equation? If you want to find that, step number 1 is you're going to look at copper from the reactant side. And then you determine with, okay, copper is an atom here, meaning it has an oxidation number of 0. And then you look at that copper ion on the product side. So this is Cu2 plus, and then we can see that it's positive 2 on it. So what do we see here? Is this an increase in oxidation number or a decrease in oxidation number? Definitely it's an increase on it. This is an increase in oxidation number. So if this is an increase in oxidation number, that means what are we looking at here? What type of reaction does copper undergo in this reaction? They say, is it oxidation or reduction? We're going to say it's what? Oxidation. Another way to also go about it is to check here. And yet, remember, I also taught you how to use your 4B table. And yet, so you can simply just go here and then make sure that you are using the 4B, right? Make sure that you are using the 4B, not the 4A. Then I said, look for those two substances that you are given, copper and silver. It's copper and silver yet. Then you are going to say, I have my copper. Where is it? Remember, I said for copper, you must always take lattice 0.34. You ignore the rest of them. Do not ever use those other ones. We only stick to this one. We have copper, and then we have ubani, UAG. I always said with the one that appears above the 4B table is the one that undergoes oxidation, and the one that appears below is the one that goes reduction. And then also remember the zigzag method, the Z method, right? I said ukuthi mangabe kuyi-oxidation moyibhala i-reduction half iqala ngapha iyale. But then reduction, when you write the reduction half, it is simply from here all the way to that side. So that means if you were to write the oxidation half yalana, it would be copper changing to copper 2 plus 2E. Right. So that would be the case then. That would be the case. If you have any question, please post them on the group before I pass. Then oxidation, ilesovela qala, reduction is the one that will be below. So it's also another way. So obviously from looking at this here, phezulu lena, you can see what, okay, that means it's oxidation. But then even from this, way simple, you say what, okay, it has an oxidation number of 0. Now it has an oxidation number of +2. That means there's an increase in oxidation number. That is what? Oxidation. So you have no excuse with that one. Okay, explain your answer. Obviously, ayiphelelanga lapho, they want you to explain. You want to say copper in the reactant side, has an oxidation number of what? Oxidation number of 0, right? And Cu2 plus in the product side has an oxidation number of what? Oxidation number of +2. Or simple enough, you can just say the oxidation number increases. The oxidation number increases from 0 to +2. We will be able to see that. And then the oxidation number increases from 0 to +2 from reactants to product. From reactants to product. Ibeka kanjalo. So as simple as that. As simple as that. Oxidation number increases from 0 to +2 from reactants to product. So that means it's undergoing oxidation. Right. 9.1.3 says formula or name of the spectator ion in the reaction. Masingafunda la, we are given this, but a clean piece of copper is placed in a solution of silver nitrate. The balanced net ionic equation now becomes like this. A spectator ion is the one that will be left out from the equation. So when we balance the equation there, that particular substance is left out. As we can see here, how did we end up having Ag plus? And then we're no longer seeing that NO3. It's because lemma break it down about Ag plus and NO3 minus. Now, you are not seeing this NO3 minus here because that's what is called a spectator ion. So a spectator ion does not change its oxidation number from the reactant side to the product side. So even if you were to carry it to this equation, you would find that the oxidation number of this would still become -1, even on the reactant side, even on the product side. We call it a spectator ion. Right? So formula or name, they want the formula or name. So obviously, you can just write the formula. NO3 minus. Reduction half reaction. Reduction half reaction. Sibuyela kuphi? Ngapha. And then we say, oh, reduction, it has to be this one. Because we've already identified here with le phezulu oxidation, the one that will be below is reduction. So reduction half reaction, what do? We just simply write this one. But then you have to be careful when you write it. Do not use this type of arrows here, this double arrow here. You need to write it as what? Ag plus E, and then you use the arrow leso, and then you say Ag. The double arrow here means it's a reversible reaction. But then if you are only showing the reduction part, it does not have to be reversible. Because once waibala is reversible, you are saying it can either be reduction or oxidation. Okay, so that's what we have there. Inshallah. So this is a very easy topic. This is a very easy topic. Ayikho into nje ecrazy abazoyibuza la. So yes, you have that, you have that. So this was for 9.1.4. Sorry for all over the place. The NO3 minus here being a spectator ion, that's the answer for 9.1.3. And then obviously here we said oxidation, right? And then that was the explanation for 9.1.2. So we had selected oxidation. Okay, so I believe we are fine with that one. Quickly note. Okay, 9.2 says sulfur dioxide SO2 is bubbled into an acidified solution of potassium permanganate as shown in the diagram below. It is observed that the solution turns from purple to colorless due to the reduction of MnO4 minus ions to Mn2 plus. So let's note that one down. They are saying MnO4 is being reduced to Mn2 plus. Izosinceda ukuthi select the correct one. During the reaction SO2 is oxidized to sulfate ions. So another statement that will help us to identify which reaction we need to take from that 4B table. Right. Awuvele uchoose noma kanjani. Now they say 9.2.1, determine the oxidation number of sulfur in SO42 minus. Now pay attention to this. They want oxidation number of sulfur in SO42 minus. Now, when you look at all of this, the 2 minus here is not for the oxygen. The 2 minus is for the whole substance. So the oxidation number of the whole substance here is what? -2. But these are some pointers that you should know. There are standard oxidation numbers. The standard oxidation numbers are for what? Oxygen and hydrogen, right? So these ones are standard. So O2 minus, the oxidation number lights always -2. H plus, oxidation number for this one is always +1. These are the two that you need to know. For hydrogen, it's always +1. For oxygen, it is always -2, right? And then basically what you don't know is the oxidation number of sulfur there. So what do? You will say sulfur mass. How many oxygens are here? There are 4 oxygens. Each oxygen carries an oxidation number of -2. And mind you, it's not this -2 here. It's for oxygen. Then we're going to equate it to the -2 ewa yonke le nto le. So basically we are saying the oxidation number of this one plus 4 times the oxidation number of oxygen from here. And yet, oxygen from here. Then equate it to what? Equal to -2. So this is x. 4 times -2 is -8 is equals to -2, and then we're going to have -2 plus 8. So x will be equals to what? +6. So that is the oxidation number. Let me show you with another one so that you understand in the biolab. NO3 minus. Again, when we look at all of this, the minus there is indicating that the oxidation number for the whole substance here, or the whole ion, is -1. We don't know the oxidation number of oxygen, of nitrogen, so we want to make it X. But we want to say how many oxygens are here? 3. Each oxygen has an oxidation number of what? -2. Makes sense now. Then I'm going to equate it to what? The -1. So here it was just a coincidence which the whole thing is -2, and then also oxygen is -2. But then understand that we equate to the number that we have here. Then this will be x. 3 times -2 is -6, equal to -1. then x is equals to -1 plus 6. Then therefore our x will become what? Positive 5. So that's how you determine the oxidation numbers. Then obviously, if you can still remember the one that we did even on Saturday, it was this one where we were trying to find the oxidation number of manganese in MnO and then of aluminum in Al2O3. How we did it is to say we already know the oxidation number of oxygen, but we don't know for manganese. So oxygen is -2. But then now, if it's like this, what do we equate it to? Remember, if it's like this, we say it is a stable substance. So that means it's equal to 0. If it's not an ion, it's a stable substance, and all stable substances have an oxidation number of 0. Then x will be equal to what? If we transpose, then x will be equal to 2, meaning the oxidation number for manganese would have to be positive 2. For aluminum, again, how did we do it? We said we don't know the oxidation number of aluminum. And here we are presented with 2 of those aluminiums. So this becomes what? 2x plus how many oxygens? 3. But each oxygen has an oxidation number of -2. Again, we are met with a stable substance, which means wamele is equated to 0. Now we have 2x is equals to positive 6 when we transpose, then divide by 2, our x becomes positive 3. That's the oxidation number of aluminium. So yes, make sure that you know how to do those. Another one that they like is this one. It is Cr2O7 2 minus, if I'm not mistaken, right? And then again here, we're going to say we are looking for chromium. They will never ask you to calculate for oxygen because oxygen is always given to be -2. Then chromium, you're going to say we have 2 chromiums, 2x plus how many oxygen atoms or ions? 7. And then each has a -2. Mind you, it's not that -2. It's the standard one. And then since all of this is equal to -2, we're going to equate to -2. And then this is 2x, -2, this is -14. When we transpose, it becomes positive 14. And then this is 2x is equals to 12. Divide by 2. Our x now becomes what? Positive 6. That's the oxidation number. So it's very simple to calculate those things. Very, very simple. You see here, define the term reduction in terms of oxidation number. In terms of oxidation number. Now you won't say reduction is the gain of electrons, or wrong. Now you have to say what? Reduction is the decrease in oxidation number. It's like when you get to law. It's like when you get to acids and bases and they ask you to define according to Arrhenius, or they ask you to define according to Lowry-Brandstad. You must know how to differentiate between the two. All right. Okay, so now I believe you have seen how to calculate the oxidation numbers. You won't be having a problem with that. Write down the oxidation half reaction for this one, right? We are on this one here. Now, obviously, in this case, that's where you need your 4B table the most, right? And then remember with sidila nan, sidila no Mn oxomela shinja yeku Mn2 plus, MnO4 minus to Mn2 plus, SO2 to SO4 2 minus. You must make sure that you select the ones that correspond to that. You don't just pick and choose anything. It has to be liabayimenshinile lapho. So, okay, we have MnO4. Where do we have MnO4 turning to Mn2 plus? There we go. Nayila. So kusho ukuthi kuzoba ile. Now, there is another one which is almost similar to Yona, but then you can see here the difference is that we don't have MnO2, we actually have MnO4. So kuzomele ube careful in terms of identifying them. You don't just identify noma yiphi, you identify the exact one. You want to see MnO4 here, and then you want to see Mn2 plus there. Okay, then we have the other one, ekhuluma ngo-SO2 and SO4 lab. So I believe it should be this one. So since it's up there, we understand why Bate SO2 changes to that. Because again, applying the Z method, i-oxidation siyibhala from la siyise ngale. A reduction from the left to the right. So that means if we had to write the oxidation half, how would the oxidation half look like? It would be SO2 plus H2O to give us what? SO4 2 minus plus 4H plus 2E. Right. And then if we were to write the reduction half, then we would have to write this one. But then our question was asking us for oxidation half. So we keep it at the oxidation half. Ubala le. Awubali le enye. Right? And then again, see the arrow that I'm using. I'm not using layup. So yes, just like that. So when you identify on the 4B table, make sure what you identify is in abakhulume ngaso lapho. So if you can check, if we can just go back again, we can see that they talked about SO2 oxidizing to SO4 2 minus. SO2 oxidizing to SO4 2 minus. Okay, right? Then what do we then have? Balanced net ionic equation using the half reaction method. If we want the balanced net ionic equation, that means the following step is that we need to also write the what? We need to also write the reduction half. How do we write the reduction half? Remember, with the reduction half, I said, do not change anything. Write it from left to right. And then 8H plus 5E to give us what? Mn2 plus 4H2O. Right. This is an interesting one. Now remember, the whole purpose of the net ionic equation is to make sure that you balance the number of what? Electrons. Right? So as we can see, kuno 5 ilangale kuno 2. We do our cross multiplication, meaning la phezulu so multiply ngo-5, la phansi so multiply ngo-2. That's what you do. Then 2 multiplied by 1 is 2. 2 multiplied by 8, this now changes to what? 16. So I'm going to use this color for all the ones that change. Yeah? And then lo 5 ilona, sometimes I'm going 2 over obani, 10, right? And then here we still have the 2. You have to be careful and check ukuthi yonke into uyayishintsha lapho. Then 2 multiplied by 4, that's going to be 8. Then let's come over here. If I say 5 multiplied by 1, I have 5 here. I also have 5 here. I have 5 here. And then 5 multiplied by 4, this will give me what here? This will give me 20. Right? And then 5 multiplied by this will give me 10. Right? So what happens is that since nalo 10E, they will cancel. But you need to be careful with this one. Not only do these ones cancel now, you also have to know to no H plus here. So what do you do in a case like this? Lo uzothatha kusho ukuthi lo H plus uzosala where there is a bigger number of those H plus. So what you actually do is you take the bigger one minus the smaller one. So that's 20H plus minus 16H plus, meaning to obviously lazy zizokhansela zonke. But then la maskip u-16 la, kusala bani? Kusala u-4. So be careful of this one. Also, this one iba affected by that. Because basically we are cancelling off izinto ezifanayo lapho. We are minusing izinto ezifanayo. So these ones are like terms, meaning I can subtract them. I can say 20H plus minus 16H plus. But then the thing with electrons, you have to make sure with akusali nix. With H plus, yes, you can remain with some, but then with the electrons, you have to make sure with when you balance, you no longer have any electrons, which is why the main focus is on balancing those electrons, is making sure we allow my electrons as olingana so that we can completely cancel them off. And then our net cell will now look like this. So remember with the net cell, zonke lezi before the arrows osibhala la. So this is 5 SO2 plus 5H2O plus 2MnO4 minus. So ngiyehlisa zonke lezi before the arrow, and then I do my arrow, ngiyehlisa zonke lezi after the arrow now. So starting with 5SO4 2 minus, and then here I'm no longer left with this 20H plus, but then 20 minus 16, I'm left with what? 4H plus, right? And then also plus what? Plus the 2Mn2 plus the what? Plus the 8H2O. Okay, so again here I am seeing another thing. These ones we can actually subtract them here, right? We can actually subtract them. And then we can say 8 minus 5. That means we're going to remain with the 3 this side. So that means on this side here, I can end up with what? Since I have 8H2O here, and then 5H2O that side, then if I cancel them out there, I end up with 5SO2, and then this one will be what? 3H2O, because they are finalists. They are finalists. So yes. Wait, didn't we have a 2 here? We had a 2 here, so that means it was supposed to be 10. Okay, no, I'm wrong. It was supposed to be 10, and then that means H2O ungap. Okay, my mistake here. We had a 10 initially, we had a 2 initially, so if we multiply it by 5, it becomes 10. So this is supposed to be 5S2O plus the 2H2O, yes. And then la izokhansela la. So lo 10 lo uzo minus lo 8, and we are left with 2 on that side. Yeah. I think that was why you were raising your hand there. Okay, how do I choose the reduction? May you please repeat the part where you choose the half reduction? The half reduction, I choose it based on what? I choose it based on this, what I'm being told here. So now in ngitshelwe yona. Bathe the reduction of MnO4 minus, note this, the reduction of MnO4 minus to Mn2 plus, the reduction of MnO4 minus to Mn2 plus. And then when I get here, that's what I want to pick. That's what I want to pick. I want to pick exactly lang zobono MnO4 are reduced to Mn2 plus. I do not take into ecishe yafana nayo. Ngithatha yona exactly, right? So I was showing you here that there is enye ecishe yafana nayo, but then you don't take that one. You see, when you look at this one here, you can see some resemblance with this one. But then this is MnO2. not MnO4 minus. So the one that you are looking for is exactly this one. That's how I get to choose that. That's how I get to choose that. Okay, so let me go over again. Let me go over it again. Then I said, number one, I chose Le because it's exactly what I'm being told, right? And then the other one is this one because they said SO2 will be oxidized to SO42 minus. Now I know with Helena, it's written from the right to the left. So it's actually true when they say this will be oxidized to that. And then here it's actually true when they say this will be reduced to that. Now, so then what do I do? First thing, I need to batenyenze ini, your oxidation half. So with the oxidation half, I take it from this side over to that side. This is SO2 plus 2H2O. Let's make sure ukuthi siyibhala kahle. Any mistake whereby awuyibhalanga kahle, you can actually be wrong. And then SO4, 2 minus, plus 4H plus 2E. Okay, this is the oxidation half. Let's get to the reduction half. With the reduction half, remember, I do not change anything. I simply write it exactly as it is after identification. Then MnO4 minus plus 8H plus 5E to give us what? To give us Mn2 plus 4H2O. Now, you want to multiply mainly because you want to balance out the what? The electrons. You always have to make sure that the electrons will completely cancel out. So how can you make sure that they cancel out? You use the cross multiplication, meaning if there is a 5 here, multiply ngaloyo 5, le phezulu. If there is a 2 here, multiply ngaloyo 2, la phansi. Why uyenza kanjalo? It's because you know 2 multiplied by 5 and 5 multiplied by 2 is okuphu 10. And that's how you will make sure that the electrons are balanced out. Okay. So if there was a 3 here, there was a 2 there, multiply ngalo 3 phezulu, multiply ngo 2 la phansi. I hope it makes sense. Then when you multiply by that 2, this is what happens. You're going to come here and multiply everything by 2. Careful on that one. You say you have 16 here. Here we have what? 10. Here sizoba nobani, naloyo 2. The 4 here, 4 times 2 will become what? 8. And then you come over to this one, multiply everything by 5. It's a 5 here. 5 multiplied by 2 will be a 10. This is what we missed out last time. Then this is 5 multiplied by less of 5 la. And then 5 multiplied by 4 kuzomele kube 20 la. Right? And then the 2 multiplied by 5, that's the 10 that we are going to get again. Now, we have achieved our goal because lezi seziyalingana, cancel out. But now, inkinga ukuthi we must then look for other like terms now. Do we have other like terms? 10H2O, 8H2O. You always have to take from the bigger side minus the smaller side. So I have 10 here, I have 8. These ones can subtract. That means I'll be left with the 2H2O here. Other like terms that I have 20 H plus here. And then also what? 16H plus. From there, I'm no longer seeing any like terms. So I'm going to say 20 minus 16. Bigger one minus smaller one. Then obviously, lezo hamba yonke. And then here, if I say 20 minus 16, I'm left with 4H plus. Then out to see Bali net cell again much. The net cell will look like this, the net cell reaction. I'm going to drop everything here. So 5 SO2. Then remember lalo 10 minus nalo 8. So kusalo 2H2O. That's what's on the left of the arrow here. Then I have to take what's on the left of the arrow on this one. 2MnO4 minus. I circle because remember ngi minus la. I circle le. And then here I have 5SO4, 2 minus. Remember, when I minus that 16, ngasala nobani? No 4. So 4H plus. And then I circle. Now I'm left with this. 2Mn, 2 plus. Lo 8 inayaga circle because ng minus la ulo 10. Then that's my net cell reaction. Yes. That's my net cell reaction. So yep. Make sure you take it down. So I believe Wuti, I have explained it well. Everyone gets it now. All right. That was it for this one. That was the last one. And then let's see. I think there was another one that we did not do during class. This one here. So here they were saying identify an oxidizing agent. In the above mentioned reaction, explain your answer by referring to the oxidation numbers. Right? So if we want to identify an oxidizing agent here, let's see. We had calculated here and we found Uguti aluminum here is what? Was it 6 that we found again when we calculate? We said 2x 3 multiplied by negative 2 equal to 0. This is 2x and then my yale became positive 6 divided by 2. X is 3. So aluminum was 3 plus. But then aluminum in this side was just 0 because it's a stable substance there. Now from 0 to 3 plus, we can see that that one is undergoing what? It's undergoing oxidation. So if it's undergoing oxidation, this is reducing agent. So it can't be that one. Then let's look at Mn. Mn here, when we calculated, we found that it was x plus negative 2 is equals to 0. Then it became positive 2. So here Mn was 2 plus, but then Mn this side is what? 0. So Mn 2 plus to 0, from 2 plus to 0, that's undergoing what? Reduction. And if it's undergoing reduction, it means that's the oxidizing what? Agent. Right. So that means here, our oxidizing agent is what? Mn. And then we're going to have to say oxidation number of Mn in MnO4, in MnO is what? Is positive 2. And on the product side, the oxidation number is what? Is 0. Right. So that means we can see that there is a decrease in oxidation number. If there is a decrease in oxidation number, that means we are dealing with what? An oxidizing agent, which is undergoing what? Reduction. So you always have to confirm with your oxidation numbers. You don't just pick and choose any that you feel like, right? So knowing already masowazi ukuthi okay, if they're talking about oxidizing agent, they're talking about the one that undergoes reduction. You can even use your 4B table. It's just a matter of knowing Lauma definition. You can even use your 4B table at this point and say, oh, let me check between Mn and aluminium. So Mn nango la, right? And then aluminium now has to be above. Okay, no. Oh, I'm using the wrong one. 4B. 4B nylon. Manganese wami Nkosi yami. There we go. Manganese below and then aluminium above, which tells you what? The one that is above on a 4B table undergoes oxidation. The one that is here undergoes what? Reduction. So as ubona lapho from Mn2 plus to Mn. From Mn2 plus to Mn. So what was the question here? Let's read. What was the question? It was asking us to do what? Identify an oxidizing agent. So your oxidizing agent is not Mn actually, it's even Mn2 plus, because it is the one that is being, it is the one whereby there will be a decrease in oxidation number from Mn2 plus to Mn. Remember, when we are talking about agents, you always have to choose the one that is on the reactant side. So the oxidation number of Mn here is Mn2 plus, and then this side it's Mn O. So this is the what you call the oxidizing agent, because it is the one that is being reduced from 2 plus to 0. So your answer is Mn2 plus. Oxidation of Mn in MnO is positive 2, and the product, the oxidation number is 0. Okay, coming to this one. Oxidation half reaction, reduction half reaction, balanced net ionic reaction. Right? So let's see, between H plus and copper there, which one? So this is what we have. We want to see which one undergoes oxidation. If we can look at this one here, check. H is positive 1 here. When it gets to this part, let's calculate the oxidation number of hydrogen here. It would be the oxidation number of hydrogen. For all of this here, this will be 0 on it, because we have 2 multiplied by positive 1 and then negative 2. So it's still positive 1 even here. So positive 1 this side, and then of hydrogen still positive 1, which makes our hydrogen ion here the spectator ion. Why is it a spectator ion? Because we can see the oxidation number of hydrogen on the left-hand side is exactly the same as the oxidation number so by ionala. Even here, hydrogen always remains positive 1. So that means that this is not our subject of interest. Let's look at copper now. Copper is from 0 to positive 2, meaning it is the one that is undergoing oxidation. And then this becomes what? Cu to give us what? Cu2 plus 2E. Then the other one should be the one at NO3 and NO. Go to your 4B table, identify exactly into zoba no NO3 minus, no NO, and see ukuthi bayibhale kanjani. Exactly like that. Exactly like that. Make sure you don't change. It doesn't change anywhere. So where is it? 9. Okay, this one is saying NO3 minus and NO2. Not exactly the same. I want you to see, I want you to be able to differentiate between 0.96 and 0.80. Siyabona ukuthi lezi zinto cishe zafana, but then you have to check carefully ukuthi bakuphi izinto ezinjani. Abazange basipho u-NO2, basipho NO. So if you check there, we had NO and NO3 minus, meaning the correct one has to be this one. You don't use that. So you have to identify the one that is exactly the same. And the one that we use for copper is obviously that one. Again, iyavumelana nale nto yethu. Again, nangu zigzag wethu. Z, see? There we go. Oxidation half izoqala ngaphi le. So this is oxidation half. Let's write it here. Oxidation half. It's Cu to give us Cu2 plus 2E. Reduction half. Take it exactly as it is. NO3 minus plus what? 4H plus. Plus 3E. To give us what? NO plus 2H2O. Then, last question itaifuna ini? In that cell. What do we do? The whole idea is making sure that we balance these ones. Cross multiply. Uno 3 phansi, uno 2 le. Kusho ukuthi as multiply phezulu ngobani? Ngo 3. As multiply la phansi ngobani? Ngo 2. Then if we say 3 multiplied by this, kuzoba bo 3 konkelana. And then le changes to 6. 3 multiplied by 2 is 6. Now so. And then here when we multiply by 2, that's 2. 4 times 2, that's going to be 8. And then 2 multiplied by Lena was 6. Now we have achieved our goal. Once sabona my electron balance lapho, we are good. Then 2. And then here we have what? 4. After cancelling out these ones, we don't see any like terms. Ayikho into efanayo lana la. So that means let's just drop everything. 3Cu on the left, and then 2NO3 minus plus 8H plus on the left. On the right of the arrow, you have 3Cu2 plus 2NO plus 4H2O. Injalo ke ungabhayisi. Injalo. So that's how you use that 4B table. As long as you can correctly identify lefana nayo ngamashi, then that's all the work. That's all the work that you do. Nothing crazy. It's just a matter of having your 4B table ubheke ukuthi le nto selector exactly the same. Then le ephezulu oxidation ephansi reduction. Then cancel izinto ekumele sicancel. Injalo. Ayijiki. So yeah, we have taken the time with that one. But then yeah, I believe because some of you been here while I was teaching this topic. So yeah, I believe now I've clarified. Even now we corner, maybe right now you have a new way of looking at it. Now you understand it fully. Okay, are we done? I believe we are done. Okay. The Z thing is a way in which we determine ukuthi is that into bengichaza yona lapho ukuthi kumele understand ukuthi when you write the oxidation half reaction it must start from this yele, just like you see here. You see here I don't start with this one and then ngigcine ngale. So the Z is telling you that if I have to write oxidation half reaction, I have to start it from the right going to the left. Right? So it has to start from the right going to the left. That's why mawubona la ngithe copper to produce copper 2 plus and 2E before ngibalance. Angithi plus 2E. So this is how I would write this one, the oxidation half. I would say Cu to give us Cu2 plus 2E. But then here it's telling us ukuthi if I want to write the reduction, I don't change anything. I simply write it from the left to the right, as we can see from here. But then don't use le usebenzisa single arrow. But then when you write the reduction half, you simply just have to write it exactly as it is. That's the Z method. That's the Z method. So it's a way to tell you ukuthi i-format ye-oxidation ne-reduction kuzomele ibe njani. So if you can actually look at it, you will realize that when we are dealing with oxidation, your electrons must always be on the right or on the product side. But when we are dealing with reduction, your electrons must always be on the left or the reactant side. That's the Z method. Hope it makes sense. Okay. Right. So done with that one. Let's look at question 8. We have acids and bases. Sulfuric acid H2O can react with water through a multi-step reaction. The two reaction below shows the multi-step reaction. Why does it undergo the multi-step or the two-step reaction? It's because most of the time we refer to H2SO4 as a diprotic acid, right? Now, what is a diprotic acid? This is an acid that donates 2 protons. This is an acid that donates 2 protons. So if it can be able to donate 2 protons, I know I'm a diprotic acid. Let me just give off my 2 protons as a soak. So it will be a step, a process to say that it will first give off its first proton or hydrogen. It becomes like that. Then from LAPO, it will continue and still give another hydrogen. Then at the end of the day, it will become SO4 2 minus. The 2 minus indicates that it has already donated 2 of its protons. Right. Now, if you want to see the difference, you see here, we are dealing with redox and acids and bases. Redox, we say we are dealing with what? Electron transfer. Which is why we are ukuthi into esifocuse kakhulu kuyo la ulo E minus. But then when we come to acids and bases, another word for acids and bases is what we call protolysis. Protolysis is what? Proton transfer. That's the difference. Both of them are reactions. Also check it topic yakhona, it falls under chemical reactions, right? Or types of reactions. But then the difference is that with the redox, it's all about transferring an electron. With an acids and bases, it's all about transferring a proton. Hence, you can even hear my definition walana bazothi an acid is a proton donor, a base is a proton accept. But then when you hear my definition walana ano electron phakathi. So here we are transferring a proton, here we are transferring an electron. But all of those fall under reactions. And then, okay, we have that. Can someone close the mic? Then 8.1.1, define an acid according to the Lowry-Brunstad model. Right. So it's not only Lowry-Brunstad lo bazokubuza ngayo, sometimes bazokubuza ngo-Arrhenius. So you have to know the definitions for acid according to Lowry-Brunstad, base according to Lowry-Brunstad, but also be able to define according to Arrhenius. I noticed the trend ukuthi abantu basanokukhohlwa leya Arrhenius. So make sure that you note it down when we look at the one for Arrhenius. So what is an Arrhenius base? This is a substance that produces hydroxide ions. When reacted with water. Or abanye bazothi in an aqueous solution. It's the same thing. Aqueous, agua, it's water, right? Then Arrhenius acid is a substance that produces hydronium ions. Hydronium ions in water or when reacted with water. Right, so that's your Arrhenius base and your Arrhenius acid. Then obviously with Lowry-Brunstad acid, we say this is an acid is a proton dome. Sonke siyayazi le siyayicula. And then a Lowry-Brunstad base, we say a base is a proton acceptor. Yes. So know your definitions. If they ever pull up with Arrhenius, then be prepared. Then is water acting as a base or an acid in reaction 1 and 2? Now, guys, this is a very good question here. And then it will also lead us to 8.1.3. Let's check. Now, in order for you to identify whether something acts as a base or an acid, check nge-conjugate acid yayo. Check ukuthi ku-product lonto leyishintshe iba yini. Remember when I was teaching you conjugate acid base pair, I said lena kuzomele ihambe nayiphi na lena. Ungarelate izinto ezingafani. You can't take H2SO4 and relate it to H3O+. Azifani lezo zinto lezo. So here the H2SO4, it went and became HSO4 minus. You can see here with begnama hydrogen I2 lasing the hydrogen A1. What is that thing telling you? It's telling you that as H2SO4, nginikele ngani hydrogen. Right, so I'm trying to zoom in so that you can see. H2SO4 and then HSO4 minus here. This is an acid. Why? Because it gave away. But then an acid will always produce a conjugate base. You can't find an acid producing another acid. So here, this is a conjugate what? Base. Now, what happens with this one? H2O, masegiwale segu H3 plus. H3O plus. Now we can see that you have gained. So, kusho ukuthi mangabe lo bekuyi-acid, kusho ukuthi uyi-base. And then loma we conjugate base, kusho ukuthi uyini? We conjugate acid. Do not complicate these things. It's not rocket science. Zinje njengoba zinjalo. Right? But now what happens here? This is where the confusion becomes. Lena iloku yi-conjugate base kanjalo. Mayiza la ayisaqhubeki ngobu-conjugate base. Seyiqhubeka as a what? As an acid. Why do we say it continues as an acid? Because now when we look at its behavior here, nalento efana nayo, we can see with man lento le isanikela le. Yabona? Then we say this is an acid, this is a what? This is a base. It is still giving away. Yabona? Bayiphulile inhliziyo mara still isanikana ngothando la ku-reaction 2. Right? Still giving. Then acid and then base again. Then this is a base. And then it has to be what? This is an acid, conjugate acid. Now, at this point, we know, guys, according to our notes, yes, they have said that water can act as an ampholyte, but it doesn't mean that water is always an ampholyte in all the cases. Water can only be an ampholyte when you observe that it acts as a base in one reaction and it acts as an acid in another reaction. But for as long as it maintains the same role, do you see this? Water is maintaining the same role in reaction 1 and 2. It acts as a what? Which is the answer that we have here. Is water acting as a base or an acid in reaction 1 and 2? We're going to say it's acting as a base. Right? Give a reason for the answer. It accepts a proton. In reaction 1, it accepts a proton, becomes hydronium ion. In reaction 2, it accepts a proton again, becomes hydronium ion. Akukho la ithi no, let me give. In this relationship, it was the receive. In this relationship again, it is the receive. Nebon. So you can't say it's an ampholyte. An ampholyte, i-base ngapha, ibuye ibe i-acid ngale. Let's look at this. It's a base on this reaction, reaction number 1. But now when we come over here, sekashintshile is now an acid, identifies as an acid. So i-ampholyte after 9, before 9 has the original gender. After 9 assumes a new gender. Right? Then write down a chemical formula of the substance that acts as an ampholyte in the above reaction. HSO4 minus. Write down a balanced chemical equation for the reaction between sulfuric acid and sodium hydrogen carbonate. Right? So obviously this one becomes a challenge if you can't write or if you don't know the chemical equation for sodium hydrogen carbonate, right? Sodium hydrogen carbonate, the way it's corner, this is a carbonate, this is a hydrogen, this is a sodium. Sulfuric acid, we all know, H2SO4, right? So that means what must you have, Dab? H2SO4 plus sodium hydrogen carbonate, right? Then obviously sekufuneka iskill sokubalansa lapho. Now this is a salt, I mean not a salt, an acid. This is an acid and a carbonate. Now from the notes that I've been sharing on acids and bases, you will know that when we react an acid and a carbonate, we always form what? Salt, water, and carbon dioxide, right? Those are the things that we know, which is their formula when we react an acid and a carbonate, right? You react an acid and anything that is a carbonate, you will always have salt, water, and carbon dioxide. So which means, how do we balance that? We are going to say our salt will be, so okay, this is the scale. Let me give you the scale. And yet I know what it will be a salt, water, and carbon dioxide, right? Now, I already know this. Wonke umuntu uyazi formula ka water and carbon dioxide. The challenge is what will be the salt that will be formed. Now, I have taken H2 already. I've taken carbon dioxide, meaning oxygen eyodwa lapho. So what should be the salt that forms there? The salt that forms will be, okay, show SO4 here. So now I would have to say Na, but then note that if I break this one down, the ion become SO4 2 minus. Na uba Na plus. Now remember in grade 10 you learn to, this is what you do. You say 2 lana, you say 1 here. And then you just cross multiply in order to form the salt. So Na uzothwala lo 2 lona, and then SO4 nangula. So this becomes Na2SO4. That becomes the salt that forms. Now it's a matter of balancing out. Now you can see due to this, says sodium I2. So how do we balance that? We put the 2 here so that the sodiums can be balanced. And then let's look at the hydrogens now. It would be 2 times 1 is 2. Then nalo 2 lo, it's 4. So that means to balance the number of hydrogens, I need to put 2 again here. Now if we can check here, everything is balanced. Hydrogens, how many? 4. Sulfur, 1. Oxygens, 4, and then 2 times 3 lapho. Also about 6 plus 4, that's 10, right? And then sodium, there's 2. And then here sodium, there is 2 on the right hand side. Sulfur is 1. Oxygens, how many? That's the 4. 2 times 2 here. 2 times 1 is 2. Okay, show it to balance this one. I also need to put 2 here. Okay, yes, 2 also here. And then let's check. 2 times 2 is 4. Plus lana is 6. And then plus lana, it's 10. Yes. And then hydrogens, how many hydrogens? 2 times 2, that's 4. How many carbons? Carbons is 2 times 1 is 2. Even lana, how many carbons? 2 times 1 is 2. So I believe everything is balanced now. HSO, NaCOH, yes, everything is balanced. Then you just have to balance like that. So, but then know that if you are taking an acid, reacting it with a carbonate, you have salt, water, and carbon dioxide. Now you start with the water and carbon dioxide and figure out how should the salt be. All right. Okay, then an eggshell contains calcium carbonate and impurities. An excess amount of standard dilute acetic acid solution of concentration 0.5 mole. So we know it's one of those calculation questions now that we're going to be dealing with. So Nilana, define a standard solution. I think we all know what a standard solution is. So if you don't know, please note it down. Standard solution is a solution of known concentration. So it's a solution whereby the concentration is known, right? So standard solution is a solution of known concentration. With definitions, you have no excuse. You must rock all the definitions there. Is a solution of known concentration. Now we have 10 marks here. It's very much possible to find in J equation is with 10 marks in J lab. Then button calculate the percentage of calcium carbonate in the eggshell. Wow. What's going on here? So, okay. They say An eggshell contains calcium carbonate and impurities, an excess amount of standard solution. You see how they write these ones. This is to tell you that you should not use this one. An excess amount of standard dilute acetic acid solution of concentration 0.5 mole and volume 250 centimeter cube is allowed to react completely with an eggshell of mass 56 gram. The equation for the reaction is given by the balanced equation. Then bathini lana, the acetic acid that remained unreacted is neutralized by 25. Is what? Neutralized. When they talk about neutralized, we know that we can use uqava lapho. And then this is what we have. So this is neutralized by 25 centimeter cube of sodium hydroxide with a concentration of this. So, but then unfortunately, we are only given the volume and concentration of the sodium hydroxide. Okay, let's see. The equation for the reaction is given by the equation below. But to calculate the percentage of sodium or of calcium carbonate in the eggshell. So this is what we have here. This is the reaction that we have. Now, when you want to win against these questions, lama question lawa qala la phansi aye phezulu. Right. So the statement that holds much importance right now is this one. The acetic acid that remained unreacted is neutralized by 25 centimeter cube. The acetic acid is kulumangan, this thing. This is acetic acid. This is what we know as acetic acid. So this is a what? This is an acid-base reaction. This is an acid and this is a base, right? Then, obviously, the first thing, we know, we already discussed this. Step number one is to do what? Calculate the number of moles. So we are starting from reaction 2. You do what? Step number 1. So with this method, if in a form told or 10 marks, you will always walk out with something. Calculate number of moles. Step 1. And then you're going to say, based on what I'm given, this is the formula that will work because I'm given volume and concentration. And then my concentration is what? 0.968. 0.968. I have N here. The volume, obviously, I will need to convert it. 25 divided by 1,000. Remember, from centimeter cube to cubic decimeters, you divide by 1,000. Then multi 25 divided by 1,000, what do you get? You get 0.025. And then when you cross multiply it, should be 0.0242 mole, right? We have calculated the number of moles. Now we know the second step. Remember, we know this is our subject of interest here. So step number 2 is to compare the molar ratio. Already la so na 2 marks la formula and then answer. Fortunately, abamakangilo because they have to distribute the 10 marks. And then molar ratio, compare molar ratio. Compare molar ratio, which means I would have to say sodium hydroxide to CH3COOH, which is the acetic acid. Now I see that the ratio is 1:1, meaning loma ku 0.0242, nalona kusomele kubo 0.0242. You have another mark for this one. So you can see you walk out with something from lab. Now, obviously, once you have that, you have the number of moles. What is the whole thing about here? We want to calculate the percentage of calcium carbonate in the eggshell, right? They said the eggshell is 56 gram. Okay, so what can we do now? We can say, but an excess amount of standard dilute acetic acid has a concentration of 0.5 mole and 250 centimeter cube. Now, let's note this one is in excess. You will see something, lab. So, let's calculate the number of moles in excess. of what? Of the acetic acid. And then ithini formula lapho? Izothi again C is equals to N over V. Our concentration, 0.5. And then N, our volume, we have 250 centimeter cube, which if we divide by 1,000, goes about 0.25. Cross multiply here, we have what? 0.125 mole. Right? So this is what we have. Now, remember, this is what? This is in excess. Right? And then what do we want to calculate? We want to calculate the number of moles that reacted. To calculate the number of moles that reacted, we can say the number of moles that were left in excess and then minus this number of moles here that were left unreacted. And then we find 0.125 minus what? 0.0242. We find that the one that was left there, the one that actually reacted, because what are we being told here? Na into besinayo initially, right? This is what was left unreacted. So kusho ukuthi manje ingakanani reactile. It's that. And now we're going to continue with this. Remember, you can only calculate the mass using the number of moles that reacted. So to then calculate that, we're going to say, okay, we want calcium carbonate. So from here, we are comparing this to that. Now calcium carbonate. So molar ratio again, CH3COOH to what? To calcium carbonate. We find that the ratio is 2:1. Meaning if we are saying this is 0.1008, then what should be this? Cross multiply here, it's going to be 2x is equals to 0.1008. Remember, mongakafiki ku final answer, the idea is round off to at least 4 decimal places. If it allows, round up to 5. But then at least 4 or 5 decimal places mongakafiki ku final answer, especially in this question. So let's say, so calculate my titration. Then when we put that in a calculator, we find 0.0504 moles, right? Then this is the one that you're going to be using to calculate the mass. So to calculate the mass of calcium carbonate, you're going to have to say N multiplied by the molar mass. So 0.0504 multiplied by molar mass of calcium carbonate, we already know it's always 100. So so at this point, you must know. Then we have our grams as 5.04 gram, right? To calculate the percentage, we have to say, but actually, actually yonke 56 gram. We want to calculate how much calcium carbonate is in the eggshell. Remember, the eggshell is not the calcium carbonate, but the eggshell contains calcium carbonate. So actually say calcium carbonate, but then actually in a calcium carbonate. We want to calculate the amount of calcium carbonate as a percentage. And then what do we do now? We're going to say percentage of calcium carbonate is that 5.04 over what? Over 56 multiplied by 100. Then we share our calculator, we find that it's only 9%. So here, 2 marks. So if you can get to this point, I'm trying to show you, Wuti, you can even score marks here without even having to complete this question. If you can get to this point, let's say you are only able to get to this point, you have half the marks. If you are able to get to the point where you calculate the what? The CH3COOH lab. If you only ended at this part, then una 3 marks. Then if you continued here, what okay, from Lana, then I have to subtract this one, you get that 1 mark. And then for using the ratios here, you will get another mark. So it's now 7. And then for calculating here, it's now 8. And then substituting here, 9 and then 10. So yeah, maybe hopefully pray that there are no such questions like these ones where you need to perform those tough calculations. You will never know. But then if there is, just have the strategy ukuthi at least to luma ma-marks lapho nalapho, there and there. So questions like this, they really take time. They really need practice and for you to be really accustomed to what's going on. But then a few practices, about 5 questions doing the same thing, you will get the gist yokuthi ziyaphi. Okay, I believe we are done with that one. Thin. Okay, so if there'll be a question whereby they want you to calculate the pH, like the one that we did there, was it on this paper? Yes, the pH. Note ukuthi the formula for pH, it's also given in your formula sheet. It's negative log H3O plus, angithi? So if you are given an acid, just simply take the concentration of that acid. Because what do we know? The concentration of hydrochloric acid, le box leli manyenze kanje, this means concentration of. That's how we read it. This is concentration of hydrochloric acid is equals to concentration of the hydronium ions. Right? So you just simply say pH is equals to negative log, and then where there is that, you put 0.1. And then you just calculate your pH like that. So easy peasy. Then you get 1, right? What you need to understand is the pH scale, angithi? Bangakubuza ukuthi is it acidic, basic, or what? So from 0 to 7, 7 to 14. 7, it's neutral, angithi? Then if your pH is greater than 7, we say now it is basic, or another way that they can use is alkaline. Mangabe pH yakhe ingaphansi kwa7, less than 7, then you say it will be acidic. Right. Okay. So I believe we are done there. Then nisikhumbuze again izinto zabo limiting reagent, all of those things. And then empirical formula. I want to rush back to this one here because I know ukuthi abantu bayikhohliwe. With this one says stoichiometric, it's recent. Okay, question 2, consider the following compounds. Define the term molecule. What is a molecule? Then also define lapho what is a molecule. So let's define. We say a molecule is a group of 2 or more atoms covalently bonded that function as a unit. Yes. So this is your definition according to your CAPS document. A group of two or more atoms covalently bonded that function as a unit. It's a molecule. Then write down the formula of the compound from the given list that has a dative covalent bond. So I was speaking about it to say the substances that have dative covalent bond, there are two. There are two that you need to pay attention to. It's when I take H2O and then I react it with H plus, and then I form what? H3O plus. This is what we call the what? The dative covalent bond. Dative covalent bond. I-dative covalent bond ifomeka manjani? So if I have to draw this in a Lewis structure, I have oxygen, it's 1, 2, 3, 4, 5, and then 6. Now, why is it 6? This is based off the periodic table, right? So periodic table here, Thomas back, we can see that carbon here is in group what? Is in group I, for oxygen, meant to say, is in group VI, which means everything in this group has what? VI means 6, and yet this has 6, everything here has 6 valence electrons. Everything in here has 5 valence electrons. Everything in here has 4 valence electrons. Everything here has 3 valence electrons. Everything here has 7 valence electrons, right? Then, show ukuthi uzokhawunta la. Uqala uzifaka clockwise like this, as you can see me. 1, 2, 3, 4, 5, 6. Because of the Roman figure 6 lapho, we show ukuthi we have 6 valence electrons. Then hydrogens would have to react where? They have to connect here. Zivala le ibase lezi la kunabomahamba yedwa. Then plus the H plus, right? Now, in order for us to have a dative covalent bond, we have to have a substance that has a lone pair or lone pairs, right? And then we also have to have what? An empty, a substance with an empty valence orbital. Substance with an empty valence orbital. Why sithi lena empty valence orbital? It's because hydrogen is in group 1. Hydrogen is supposed to have 1 electron. But when we say it's H plus, it means that it's even missing that 1 electron. Lo plus lo indicate loss of electron, right? So if this is H plus, that means this hydrogen ion does not have an electron. It's missing that 1 electron that it's supposed to have. So meaning if it doesn't even have that 1 electron, it has an empty valence orbital. Now what happens is that this thing, lene empty valence orbital, will now connect itself to the lone pairs, meaning ukuthi iyoza nge-mentality yokuthi izobenefita from oxygen. Remember, a covalent bond is a bond whereby kuba ineka-neka. I come with an electron, you also come with an electron. But this one is a different case with this hydrogen. All the 2 electrons will come from the oxygen, and hydrogen will not have anything to offer. That's a dative covalent bond. And then we yenza kanje. Mabangathi uyi-draw. This is an example of a dative covalent bond, right? So meaning our answer here should be what? The answer to that question that we've been asked here, it's we want to select what? H3O plus. Okay, another one that can appear to be a dative covalent bond is this one. NH3 plus H plus. Right. We are not saying NH3 is the dative covalent bond. What's the dative covalent bond? It's actually money. NH4 plus. This is the one that is a dative covalent bond. Here the same case goes. We have nitrogen, which is in what group? According to our periodic table, we can see nitrogen is in group 15 with a valence electron of V5. Everything in here has a valence electron of 5. Meaning, what do? 1, 2, 3, 4, then 5. Then lama hydrogen I3 azo reactor group, azo connector la kubo mahamba yedwa. Right? So note that I show dots and crosses. That's your Lewis diagram. And then this has to react with the H plus. Now, how does this become a dative covalent bond? Because this hydrogen with an empty orbital, empty valence orbital, and then this one here with a lone pair, it means ukuthi wena hydrogen uzoconnecta lapha kule lone pair. Then here we still have what we had. Then we valelela uthi plus. So what is this called? Ammonium ion. What is this one called? Ammonia. This is what? Hydrogen ion. Uleyana, this one is called H3O plus, acids and bases sesikhulume ngayo. Hydronium ion. So those are the two dative covalent bonds you will see. It's either this or that. That's it. Ayikho enye. It's either basokunika leya or le. Okay. Ionic bonds. Now, when we are talking about ionic bonds, to confirm within Dharma ionic bonds, but then also, if you saw with the notes that I sent you already, you have seen, if you have went through the notes already, you have seen what they've given this one as an example of what has ionic bonds. So it's sodium chloride. Then if it's ionic bonds, it's the one that has ion dipole forces again. So sodium chloride. Draw the Lewis structure for the following molecules, NH3. So we have seen it's 1, 2, 3, 4, and then 5. Bafuna lena ngithi. So you just put your hydrogens like this. And then you are done. That's your Lewis structure. Make sure ukuthi you indicate dot and crosses. Ungazenza ama-dots way-2 or uzenza ama-crosses way-2. Dot and crosses. So cross for the other one and then dot for the other one. Then HCN. So you should be able to make what's inside here, the central atom. So this is carbon here, and carbon should have what? 4 electrons. So this is where it gets tricky, you must know. So Gala, try to indicate them individually. You have your carbon, you have your nitrogen this side, which we're going to say 1, 2, 3, 4, and then 5. And then this side we have hydrogen, which hydrogen only has 1. Now, this is not how you draw it, but then I'm trying to show you something. Mawungabheka this side, lo usifunela intombi eyodwa lo, because now you hamba i1. Right? Laba bayi3 abashimile bafuna intombi eziwu3. So kusho ukuthi lapha kuzomela beze la. Yabona? Nalaba bonke bazohlangana le. You see? So they will meet in this one place. then this is how you are supposed to draw it. Uzothi dot lana, le 3 yonke leso line la, endaweni eyi-1, forming a triple bond. And then hydrogen wakho makeza lana, uza ne-electron. Nitrogen, mayiza lana, nayi le 3, izodonseka ngapha. And then you still have your lone pair here. Then this is what you should draw. So what is this? This is a triple bond. Right. This is a single bond. So Marama count a number of bonds. This is one bond. This is also another bond. So you don't have 4 bonds. You actually have what? 2 bonds. Why? Because lena ihlangana yonke endaweni eyi-1. So this is a bond order known as triple bond. So, but then all in all, you have one pair of bond and another pair of bond. How many lone pairs of electrons are in one molecule of NH3? When we check this, we can see there's only one, right? How many lone pairs of electrons are in one molecule of NH3? There's only one lone pair. You don't say 2 when they're talking about a pair. Angithi bakhuluma ngazo zoyi-2 kanjalo. So it's one pair. Then is BCl3 a polar or non-polar molecule? Right? So BCl3 has what we call is a trigonal. Is a trigonal planar. Yes, trigonal planar shape. It's like this. Okay. It goes B, Cl, and then Cl, Cl. Meaning in that way, there's even distribution of charges like this. So it is a non-polar molecule. We can say it's a non-polar molecule. Non-polar. Explain your answer by referring to the molecular shape and polarity of the bonds in the molecule. The molecular shape and polarity of the bonds. Make sure which is equal so that you get marks. So what are we going to say? For 2.4 now, we're going to say BCl3 has a trigonal planar shape. Geometry or shape. Which means there is even distribution. There is even distribution of charges as the shape is symmetrical. But the polarity of the bonds are polar bonds. And then how do you confirm that? By calculating change in En. So you'll say En of fluorine minus electronegativity of hydrogen. Remember, you take the bigger one minus the smaller one. So you go to your periodic table. This is how you find lezo zinto lezo. Uzwa kuchlorine. Masikhuluma nge-electronegativity, sikhuluma ngale number. You say 3.0, and then you go for the one yaga hydrogen. Na ya lapha ubani? I mean yaga boron, not hydrogen. So na yaga boron, it's 2.0. So you want to say 3.0 minus 2.0. So this is boron, BCl. Okay, 3.0 minus 2.0 is what? 1.0, which confirms to us that we have what? Polar bonds. Remember, for as long as your En is greater than 0, you have polar bonds. And then when your En starts to be greater than 2,1, you have ionic bonds. And then when your En is equal to 0, you have non-polar bonds. Zazi lezinto lezo. So your change in electronegativity is 0, you have non-polar bonds. Your change in En is greater than 0, you have polar bonds. Your change in En is greater than 2.1, you have ionic bonds. Right. Njalo-ke, guys. So, yes. Take it down, take it down. Okay. I think we are fine with that. Right. Then the graph below shows the relationship between potential energy and the internuclear distance between two hydrogen atoms. Now, you must always remember, bathanda nokubuza le question, maybe bashawo X la, but le distance le imele. This distance here is for what? Is for bond length, right? They ever pull up with something like that? No. And then sometimes they will say Y on this one and they say label Y. Lena emailin, bond NH, which is what they want you to define here. Define the term bond NH. What is bond NH now? So we are going to say bond energy. Bond energy. So it is the energy needed to break 1 mole of a compound's molecule into separate atoms. See? So it is the energy needed to break 1 mole of a compound's molecule into separate atoms. So that is bond energy. So know that definition by hand. It is the energy needed to break 1 mole of a compound's molecule into separate atoms. Okay, then which compound A, B, or C on the graph represents the point of maximum force of attraction between the nuclei of two hydrogen atoms? The point of maximum force of attraction is always represented by the bond energy. Right. So this is that energy. This is what we need to overcome so that we can separate those. We can separate the molecules into separate atoms. right? So that we can break 1 mole of a compound's molecule into separate atoms. So that means we will say that part is indicated by what? By B. It's indicated by B. So for 2.5.2, it's B. 2.5.1 was this. Okay. Then, so unote-ke lapho, this part here going down is bond energy, and then from here up until leyo part le engena la phakathi, it's bond length. Then consider the following table. Which one of the bonds shown in the table above will have the shortest bond length? The shortest bond length. Remember, when we were talking relationships, we said bond order. When we are talking about bond order, sikhuluma ngani? Whether we have single bonds, double bonds, or triple bonds. That is what we refer to as what? As bond order. Single bond, double bond, triple bond, right? Then, what do we have here? We know that the relationship between bond order and bond length is what? Inversely proportional. So meaning, the greater the bond order, the shorter the bond length. And then, another type of relationship that you should consider is bond order will be directly proportional to what? To bond energy. So the greater the bond order, the greater the bond energy. Remember, my surrogate is single bond, double bond, triple bond. The bond order is increasing, just like we see here. Now, what do you notice? As the bond order increases, what happens to the bond energy? It also increases. But then also, again, we know that the relationship between bond energy and bond length is what? Inversely proportional. So a bond energy might look, we're expecting our to do what? To increase. So meaning which one of the bonds be shown in the table above will have the shortest bond length? It has to be triple bond between carbons. Give a reason for your answer. It has the highest bond energy and therefore will have what? And therefore will have the shortest bond length. Based off of what? Based off this relationship. This relationship. Bond energy is inversely proportional to bond length. So if it has the greatest bond energy, it translates that it will have the shortest bond length. Injalo. So anlali kulawo ma-question yayibona i-20 marks lesibhekene nayo lapha. 20. So you should know ukuthi this is serious business. This is serious business. So you go and browse on those notes then on this. Okay, question 3. Consider the list of 6 substances with their formulae and boiling points in the table below. Now they say define the term boiling point. You must know how to define boiling point according to the way bayifuna ngakhona lapho, angithi. So ungayenza bo boiling point is when a liquid changes to a gas. Okufaka wrong lapho. Faka wrong bangabheki nokuthi ubani. So how do we define a boiling point the way they want? You say boiling point is the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. Yes. So is the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. Now you can see with Tilana, you can actually usitholela ama-marks on those topics where you don't have to calculate. If you know you have a problem with your stoichiometry to this point, then your best chance of passing this exam is making sure ukuthi kulezinto lezi zama-notes, you always take your marks. If you know ukuthi stoichiometric calculations are a problem, right? Your only best chance is to make sure ukuthi on all these topics whereby you have to focus on ama notes and all those things, you know ama notes will go very well. By definition, you know all those things. Explain why the boiling point of iodine is so much higher than that of bromine by referring to the intermolecular forces present in each substance, right? Then we have spoken about this, right? If we look at bromine and iodine, these are what we call what? Diatomic molecules, right? And then I said all diatomic molecules, they have what? London forces, right? All diatomic molecules have London forces. Then NH3 and H2O, these ones, they have what? Hydrogen bonds. Nalena, OH no OH nalena, hydrogen bonds, right? So basically, if you see a hydrogen either reacting with an oxygen, a fluorine, or a nitrogen, the type of intermolecular forces present there are what? Hydrogen bonds. Then with diatomic molecules sikhuluma ngezinto ezifana nabo Br2, Cl2, I2, N2. You get the idea. O2, H2. Lezi eziphinda-phindayo. So diatomic molecules or anything that is a non-polar molecule. Once you identify with lonto it's a non-polar molecule, then just know that it is what? London forces. Then the rest that I did not mention will now have to be what? Dipole-dipole, like this one. Dipole-dipole force. So once you know how to identify London forces and hydrogen bonds, anything that does not fall between London or hydrogen bonds can either be dipole-dipole or ion dipole, right? Then explain why the boiling point of iodine is so much higher than that of bromine by referring to the intermolecular forces present in each substance. Now, this is how we go about it. We're going to say both Br2 and I2 have what? Have London forces. Start with the type of intermolecular forces on it. But then, remember I said, when you are comparing isn't the same intermolecular forces. When you are comparing things of same intermolecular forces, you have to use the ISCE method, which is you identify the type of intermolecular forces, you speak of the structure, you compare the type of intermolecular forces, and then you speak of the energy that is required to overcome those intermolecular forces. So Zote, both Br2 and I2 have London forces. But now, obviously, if you consult your periodic table, you need your molecular mass to confirm this. And yet, so remember, if they have the same type of intermolecular forces, it means it difference is over on what? On the molecular mass. Now, if you can check iodine, I think it's something like 127. Where is it? Iodine. Ukuphi kwedine? Okay, Nyla. Yes, this is iodine, 127, right? So if it's I2, then we know that the molecular mass is 2 times 127. So which means 2 multiplied by 127 is 256 grams per mole. Compare it with Br2. Bromine is where? Br. It's here, 8, just above. So 8 multiplied by 2, it's 160 grams per mole. Now we can see that I2 has a greater molecular mass than Br2. That's the structure or the size. S is for structure or size or surface area, right? So we're going to say I2 has a larger molecular mass than what? Than Br2. Follow this template, guys. Than Br2, meaning that the London forces in what? The London forces in I2 are stronger than those in what? Than those in Br2. Last point is energy. More energy is required. So you see it's 4 marks and I want 4 points. More energy is required to overcome the London forces in I2. And then your final conclusion, does I2 will, or does I2 have, does I2 has a higher boiling point? Inshallah. 4 points, 4 marks. The last statement is just the final nail in the coffin. So ubuya ubatshela loo nto le abakubuza yona. Right? So you follow the what? ISCE method, which means identify type of intermolecular forces. Speak of the size of molecules. Compare strengths of intermolecular forces. And then speak of the energy required to overcome intermolecular forces. Enjalo, guys. It's like that. Don't overcomplicate it. Simple, straightforward things. Both Br2 and I2 have London forces. Identification of intermolecular forces. I2 has a larger molecular mass than Br2. We have spoken about the size of the molecules. The London forces in I2 are stronger than those in Br2. You have compared the strength of the intermolecular forces. More energy is required to overcome the London forces in iodine. You have spoken about the energy required to overcome the intermolecular forces. Then you conclude, thus iodine has a higher boiling point. Then bathi ke manje. Here is another one. Compare ammonia and phosphine and explain the difference in their boiling points by referring to the intermolecular forces present in each substance. Now, when we look at ammonia, we said ammonia has what? Hydrogen bonds. But phosphine here has what? Dipole-dipole forces. Now we are comparing compounds that have what? Different intermolecular forces. Now, what is the strategy with the ones that have different intermolecular forces? It's ICE. You no longer use ISCE, it's now ICE, whereby now you have to what? Identify type of intermolecular forces in each compound or molecule. And then here, compare the strength of the two intermolecular forces. And then here, speak of the energy required to overcome the intermolecular forces. There is no need, note this, there is no need to talk about molecular mass. If you are already comparing things that have different intermolecular forces, you have no business talking about their molecular mass because that's not the independent variable there. That's not the factor that is causing those difference in boiling points. The factor here is that A1 in a boiling point, I mean, my intermolecular forces are stronger than the other one. So if you can even check, you can find that ammonia has a smaller molecular mass than pH3. But then you find that when you compare, this one still has a higher boiling point. So it's not about size in this one. It's about the strength of the intermolecular forces. So nakhona melu understand nendaba ama-negative answers angithi. We know that this one is bigger and this one is small. So singaphazamiswa ukuthi late negative 87.7. In terms of negative values, we know that this one is bigger than that one. Okay, so how do we follow this format now? The ICE format. So nakhona lapho kumele sithole 4 marks. Still follow the same format. ICE this time around. We're going to say NH3 has hydrogen bonds. And then pH3 has dipole-dipole forces. Now, because we have identified 2 different intermolecular forces, they are supposed to give you a mark for each one of them. So you see, even if we have ICE, which is like 3 points, it's still going to make up 4 because Lena is by 2 marks already. Then we're going to say hydrogen bonds are stronger than what? Are stronger than dipole-dipole forces. So here, if you can follow the method, it's chai. Hydrogen bonds are stronger than dipole-dipole forces, which means more energy is required to overcome the hydrogen bonds. The hydrogen bonds in NH3. And then, thus, NH3 has a higher boiling point. Clean. Clean. Shangimak. The Nayai conclusion. So you see, you play with these things. You play with these things. So no excuse there. There's no calculation, simply just a method of studying. Knowing knowing how to follow that format. ICE applies if we are dealing with what? Molecules of different intermolecular forces. ISCE applies if we are dealing with what? Molecules. And even in grade 12, I've been telling you, even class in grade 12, the topic will be called physical properties. Isobinch. Molecules of the same intermolecular forces. So we bamba from now, then grade 12, it's a smooth sailing. Okay, you find the term vapor pressure. I hinted on it ngati I-vapor pressure nayo yenye definition ekumele niyazi. So I picked this question paper because I wanted to emphasize that point ukuthi ningaclaim u-boiling point kuphela. Ningaclaim u-boiling point kuphela. No vapor pressure ukhona, right? No melting point ukhona. So vapor pressure we say this is the pressure exerted by a vapor at equilibrium. This is vapor, guys. By a vapor at equilibrium with its liquid in a closed system. Yes. So this one can be a little bit tricky to remember, but then yeah, just we balaga you should be able to memorize it. Vapor pressure, the pressure exerted by vapor at equilibrium with its liquid in a closed system. The pressure exerted by vapor at equilibrium with its liquid in a closed system. I don't want you to be losing my definitions. If you want 3 marks, you want to pass nje kalula kanjalo, you should never play with definitions. Make sure with ayikho definition nje kuphazamisayo lapho. Which substance in the table above will have the lowest rate of evaporation? Guys, when they're talking about rate of evaporation, this is basically vapor pressure. Ningabi nokutatazela, right? So they're asking which one will have a lower vapor pressure. Right. So they just decided to write it in another form, but lowest rate of evaporation. Right. Which one again? If we are looking for the one with the lower vapor pressure, that means according to the relationship Lascelles and I remember, intermolecular forces are directly proportional to boiling point. Intermolecular forces directly proportional to melting point, but intermolecular forces are inversely proportional to vapor pressure. Sabuya futhi sathi relationship its boiling point is directly proportional to melting point, but boiling point inversely proportional to vapor pressure, which melting point also is inversely proportional to vapor pressure. This is what we've been speaking about, right? Then, if we are looking for the one with the lowest vapor pressure, it means according to the table, it translates to what? It translates to the one with the what? Highest boiling point. So we want to check and see which one is the highest boiling point. And we can all agree with H2O. We all phezulu with a boiling point of 100. So, and then give a reason. So we're going to say it's H2O, and then we get a mark for that, meaning reason yethu, it's 2 marks. We're going to say it has hydrogen bonds, which are the strongest intermolecular forces. So remember, I'm stretching it out because it's 2 marks. Otherwise, it's because it has a higher boiling point. So now I want that 2 marks. It has hydrogen bonds, which are the strongest intermolecular forces. Ungabhali IMF, mawubhala lapho, bhala iphelele intermolecular forces. Then it has hydrogen bonds, which are the strongest intermolecular forces. And then again, that means, which means it has the highest boiling point. Yes. So I'm stretching it out so that I can get there 2 marks. Always have this. Remember, I taught you that skill to say with Begama marks wakho. Khona la ubona khona ukuthi it's not necessary ukuthi uze ushaye indendende lapho. Khona la ubona khona ukuthi hey, mara mangavele ngithi it has the highest boiling point for 3 marks ngiyeba ngiphe yona. Right? So you have to come up with a way to say, to also mention the intermolecular forces and say it has hydrogen bonds, which are the strongest intermolecular forces, which means it has the highest boiling point. But let's say we must identify and then give a reason, and it was only 2 marks, then it would be enough to say H2O, it has the highest boiling point. So use your discretion when dealing with those questions. Explain why iodine is not soluble in water by referring to the intermolecular forces in each substance. This question is repeating itself. It's the one that we answered, what you call. We said like dissolves in like, and it. So it was here. We said, yes, explain in terms of intermolecular forces why solid iodine does not dissolve in water. And then how do we respond to that? So, sizobabekela yona kanje. I2, which is iodine, I2 molecules are nonpolar and have London forces. And have London forces. And then H2O molecules are polar and have hydrogen bonds. Polar and nonpolar substances do not mix because of the rule that says like dissolves in like. So they don't have the same type of, they don't have the same type of intermolecular forces, London force hydrogen bonds. Again, it's also a matter that this is nonpolar and the other one is polar. So you have explained. 1, 2, 3. I2 molecules are nonpolar and have London forces. H2O molecules are polar and have hydrogen bonds. Polar and nonpolar substances do not mix. So if it was a polar with a polar, yes. A nonpolar with a nonpolar, yes. So even with these questions, you can see with Ilendolama cut and paste, they are constantly repeating the same questions over and over again. So once you can understand Ilona, format yakho and know how to do those questions, then you are gone. It's just a matter of practicing with your question papers. Even from now on, starting from now on, going to grade 12, I have already exposed you to the method of passing. It's just a matter of familiarizing yourself with our question paper, seeing all those questions over and over again. Then you gain the confidence to say, oh, lama question lawa hlezi aphuma kanje. Okay. Yeah, then this one, nayo, it's enye hlezi vela the same way. A group of learners investigate the relationship between the pressure and volume of an enclosed nitrogen gas of fixed mass at 25 degrees Celsius. They record the volume of the gas for different pressures in the table, right? Name and state the gas law being investigated, right? So we know it's Boyle's law. And then you define Boyle's law. So 1 mark for saying Boyle's law, another 2 marks for having to define Boyle's law. So sizothini lapho masiyidefine the pressure of an enclosed gas. So Boyle's law states that the pressure of an enclosed gas is inversely proportional to the volume it occupies. To the volume it occupies at constant temperature. Make sure ukuthi zikhona zonke lezo zinto lezo at constant temperature. Yes. Now, determine the numerical value of x and y. As we can see, bayenzeni allowed to get these values. To get these values, it's 1 over v. So that means they say 1 over all of this. So if you can confirm that was 0.0, if you can say 1 over 43, it should tell you that it should give you that 0.02 meant to say. 1 over 43, 0.02. Meaning if in Nalana to find x, you need to say 1 over 27, just like they did here. So round off to 2 decimal places. 1 over 27, it's 0.04 because it is 0.37. So 0.04. 0.04. Then here you'd have to say y is 1 over 18. Round off it to 2 decimal places. Nakon. So 0.06 to 2 decimal places. So that's your value for x and y. That's all you needed to do. Write down the mathematical relationship between pressure and volume. We know that pressure is inversely proportional to volume. So this is how you write it as a mathematical relationship. This means inversely. Once you get 1 over something, it means inversely proportional. So that's your 4.3. So pressure is inversely proportional to volume. For this investigation, write down the 2 control variables. Sikhulumile ngaloko. Sithe the 2 control variables, if you want to remember them, remember this formula here. It's your number of moles and your temperature. So N, number of moles, and then T, temperature. Right. So your number of moles and temperature are always the 2 control variables. Or if you don't want to write number of moles of a gas, they can even accept mass of the gas. Mass of the gas, they can accept that one. Because remember, even the N here can change to mass over the molar mass. An investigative question. What would be the investigative question? Guys, any investigative question must start up with the word, what is the relationship? A powerful investigative question must start up with, what is the relationship? Abo how, nabo who, nabo in bayek. What is the relationship? So 4.4.2, what is the relationship between pressure of an enclosed gas and the volume? Bese ufake question mark because it's a question, angithi? Yes. So what is the, so now it should involve your dependent variable and your independent variable, angithi? So what is the relationship between pressure of an enclosed gas and the volume? And remember, I did speak about indaba zokuthi to understand ukuthi sometimes it can be pressure versus volume, angithi? You can have your pressure here, kPa, and then your volume here, centimeter cube. And then it goes like that. Or you can even still have the same relationship, but then they decide to put pressure here in centimeter cube and then volume here. Ungakremi ukuthi yohlezi kuyi-pressure ngale kuyi-volume, no. So, or kPa here, centimeter cube. Yeah. So this will still give you inversely proportional, right? So you can have those ones. So kuzohluka ngokuthi yenzakaleni. If i-pressure say like that means pressure now is becoming the dependent variable, the volume is the independent. But mase solve volume is the dependent, and then this is the independent. So ungakrip, look at what you are given. So this is when they say draw a pressure versus volume, this is what you draw. When they say draw a volume versus pressure, this is what you draw. Siyahluka lezo zinto lezo. Then even nala siyahluka la. When they start to be directly proportional, you can have your 1 over V here and then pressure there. Or you can have your 1 over V lapha, then pressure this side. Or you can even have 1 over pressure then volume. Yayenzeka. So any that they ask you to draw. So this is a pressure versus 1 over V. This is 1 over V versus pressure. Or you can have a volume versus 1 over P. Ngokuthi bazobe bakuphinde njani. Now the statement will be clear as to which one you should draw. The statement will forever be clear. You read your statement, it will always be clear. Draw a graph of pressure versus 1 over V. Yes, that's what we are saying. Draw a graph of pressure versus 1 over V. Kusho ukuthi kuzosebenza loku naloku. You don't mind these ones. You don't use these ones. It's only pressure and this one. Now, obviously, plot lapho, at the end of the day, you should have an increasing graph. The end of the day, this is the type of graph that you want. Then maybe 0.02 lapha, 0.04 lapha, and then followed by 0.06. Then we have 0.08. So yeah, uzoplotha lapho the way sizoplotheka ngakhona. Obviously, I cannot draw something that is precise here. Then ube ne-interval ke, ungaveli ujump ama-numbers like that. Like have even spaces. You see even nalana. I must space evenly. Kwamele kulingane la mangispace la. So even nalana choose the-interval. Mawuhamba ngabo 20, hamba ngabo 20. 20, 40, 60, 80, 100. Interval yakho mayengathi 20 besithi 60 besithi ithi 80 besithi 150. No. There must be a consistent interval, and then also the distance from one number to another must be equal. Even nalana kwamele zibe equal. So I can say 0.02, then 0.04, 0.06, 0.08. So I must make sure which is the equal lab. Right. Then use the graph to determine the value of the gas at 68 kilopascals. Obviously, masoyidrawile loo nto leyo, kuzomele uyidonse from lapho ngithi. Kuzomele uyidonse from loyo 68, maybe uzo to 68 to somewhere bomala. And then kuzomele we stretch it out lapho. See what it touches here, and then mayiqeda ukutoucha, you'll have to bend it down, right, to see ukuthi kunikani lapho. So according to the memo, the value that they found is 0.034. So your 1 over V value is 0.034. But remember, they want the volume. So 1 over V is equals to 0.034. You cross multiply here. You have 1 is equals to 0.034, and then V. Divide both sides by 0.034. 0.034, because remember, say volume le inverse here volume. This is the inverse of volume. So awukaqedi. you'd have to calculate your volume, then divide by V, by that number, you get that your volume is 29.41 centimeter cube. Right. So that's what you need to know. Pressure versus 1 over V, you'll have a directly proportional graph, an increasing graph like that. But pressure versus volume, you'll have a inversely proportional graph, which will be decreasing. Under which conditions of temperature and pressure will real gas deviate from ideal gas behavior? We've spoken about this. We said the question they can either ask you in terms of when will it deviate, when will it behave more like a real gas. So you must be able to answer that question in those two formats, right? So if you want to know when it deviates, so now, yeah, behaves like an ideal gas, and then deviates from ideal gas. When does a real gas behave like an ideal gas? For as long as the temperature is high. When there's high temperatures and then low pressure. When does it deviate, meaning it starts not to act like an ideal gas? Whenever you keep your temperatures low, but then you keep a high pressure. So meaning to answer that question, AEP block correct. So when there's low temperature and high pressure, those are the two conditions whereby you'll have your real gas deviating from ideal gas behavior. Then use the kinetic molecular theory, KMT, to explain the effect of an increase in temperature on the pressure of a gas. How does an increase in temperature affect the pressure of a gas? So we say when temperature increases, when temperature increases, the average kinetic energy, remember, temperature is directly proportional to the EK average, right? So the average kinetic energy of the particles increases. And then the particles move faster. Because now it says in a kinetic energy, remember kinetic energy is the energy of movement. There will be more number of collisions between the particles. When number of collisions increases, the pressure also increases. Yes. So that's how we explain that. How many marks? 4 marks. Yes. When temperature increases, the average kinetic energy of the particles increases. The particles move faster. More number of collisions between the particles. When number of collisions increases, the pressure must also increase. So injalo, screenshot faster. Okay. Then question 5 says define the term activation energy. We've spoken about that activation energy is the minimum energy required to start a chemical reaction. Then is the above reaction endothermic or exothermic? Let's check. Based on the heat of the reactant and the activation energy, and the heat of the reaction being negative here, heat of reaction is negative, meaning this would have to be what? Exothermic. If enthalpy change here was positive, then we're going to say end on it. But then because our enthalpy is less than 0, we are going to say exo. Give a reason for the answer. Enthalpy is less than 0. Calculate the heat of the product. We are given the heat of the reactants and the enthalpy then. So enthalpy change, we know that it's energy of the product or the heat of the product. Heat of products minus heat of reactants. So enthalpy is negative 7.28. Heat of products, that's what we want. But we are given heat of reactants, it's 26.6. So how do we get the heat of the product? By just saying negative 7.28 plus your 26.6 when masses transpose. Therefore, our heat of the products will be what? We say negative 7.28 plus 26.6, we get what? 19.32 kilojoules per mole. Yes. Right. And then you have calculated. Then, yeah, these ones are just easy questions. Draw the potential energy versus cost of reaction graph for the above reaction. On the graph, indicate the value of the heat of reactants, the heat of the product, energy at the activated complex, and then the heat of the reaction, right? So, note this. It's an exothermic graph, meaning it must start from above there and then go all the way down like this. And then we have our activation energy. Activation energy, guys, understand. Activation energy, it's always from the reactants to the product. Always. So if you have an exothermic, izoqala la because ama reactants waqala le. But if you have an endothermic, izoqala phi. It's supposed to start from down here. So your activation energy when you have an endothermic graph starts from here going down up there, which is what we know. With the endothermic has a higher activation energy because it starts all the way from below here on the reactants and then all the way up until the activated complex. But magui exo, it has a lower activation energy because it starts from up here, activated complex. So know that, know how to indicate your activation energy. So this is EA for activation energy, and then it's what? 6.73 kilojoules per mole. Okay, then what is the heat of the reactants? 26.6. What is the heat of the product? Let's do a calculator. 19.32. 19.32. And then we know that the distance between the reactants and the product, it's what we know as your enthalpy change, which is equals to what? Negative 7.28 kilojoules per mole. So that's your enthalpy. If you wanted to calculate the activated complex, understand this. Activated complex can be calculated by saying what? by saying NH of the reactant plus the activation NH, right? And then if you want to calculate activation energy, it can be calculated by saying activated complex minus NH of the reactants. So if you can check here, I just made EA the subject of the formula from that. So right now what we don't have is the activated complex. Tata logo gla plus enalogo. So it's like 26.6 plus 6.73. Then you get what? 33.33. So see, that's how you deal with those. Isebenza kanjalo, guys. Then on the same graph drawn in question 5.4, use a dotted line and draw the shape of the graph when a catalyst is added to the original reaction. Yes, guys, in the book, add the catalyst. Understand this. When you add a catalyst, we color from laguma reactants. The NH of the reactants will not change, and the NH of the product will not change. All you do is this. Make sure ukuthi iqala lapho kuma reactants iphinde iphelela la kuma products like this. You don't draw it below or above your product line or your reactant line, because activation NH, catalyst lowers the activation NH. It does not change the enthalpy change, the heat of reaction. Nothing will be done to the heat of reaction. I think they asked that question on that paper we were doing, Lapobate. What effect will the catalyst have? So this is it. How will the addition of a catalyst affect the following? Right? Only increase, decrease, or remain the same. How will it affect the activation energy? It lowers the activation energy, so the activation energy decreases. But how does it affect the heat of reaction? This will remain the same. And yet, this will remain the same. So note that the only effect that the catalyst has is on the activation energy. Now, mabate enthalpy. Enthalpy, guys, this is heat of reaction. They can say enthalpy, they can say heat of reaction. Change in enthalpy or heat of reaction. In day one, change in enthalpy manje. It's still that same thing, delta H, heat of reaction. So, ujwayele indlela ama-question kwe-exam abuzwa ngawo. K. So this is how you indicate that catalyst. So we can see that the activation energy has been lowered, which of course it results in the activated complex also being lower. Because remember, activation energy is activated complex minus energy of the reactant. Since the energy of the reactant does not change, we know that what influences the activation energy is the change in the activated complex. If the activated complex becomes smaller, that means we are saying with it's now easier to convert a reactant to product. Makes sense. Hope it does. Okay, then yeah, I think with these ones now we are fine. These are calculations. I don't believe people still want me to remind them of empirical formulas and that. But let me ask. Should we continue or try? With the empirical formulas and all that thing. When you look at those questions, do you see anything interesting that you would like us to do? Pendulan, do we continue or try, guys? You still want this? Limiting reagents and all that. Should I remind you of those things? Bathuleke bandleni. Okay, let me just assume people do it. You find the term empirical formula. This is the simplest whole number ratio of all the elements in a compound. Or abanye bathi of all the atoms in a compound. Still the same thing. Then determine by calculation the empirical formula. So in this case here, we have 54.55% carbon, and then 9.09% hydrogen, and then 36.36% oxygen. The number of moles of carbon is mass over the molar mass. Our mass is 54.55 over what? 12. And then hydrogen is mass over the molar mass. It's going to be 9.09 over 1. 9.09 obviously here. Oxygen mass over the molar mass, 36.36 over 16. Then 54.55 divided by 12. That's 4.5458. Remember it, Dingte. Make sure that you at least round off to 4 decimal places before the final answer. So this is 2.2725. Then the next step is to do what? Divide by the smallest number of moles. Then to find the ratio of carbon, is that 4.5458 divided by 2.2725. So 4.5458, 2.2725. We get what? 2. For hydrogen, we have 9.09 divided by 2.2725. 2.2725, which will give us exactly 4. And then 2.2725 divided by 2.2725. Then our oxygen is 1. Therefore, it means our empirical formula is C2H4 and then O. Yebo. That's it. That's it. Then Determine the molecular formula. Now we are given that the molar mass of the compound is 88 grams per mole, which we do know from here. We should calculate the molar mass of the empirical formula. So molar mass of this C2H4O will be what? 2 multiplied by 12, 4 multiplied by 1 plus 16. So 2 multiplied by 12 plus 4 times 1 plus 16. This gives us what? 44 grams per mole. Right? Then what do we do with that 44 grams per mole? We divide it to this 88. 88 divided by 44, that's 2. Then in order to then come up with the molecular formula, we'd have to multiply 2 to the empirical formula that we have. So njengoba ku-C2H4O, it's now going to be C4H8O2. That becomes our molecular formula now. So everything multiplied by 2. Then yes, do not forget those ones. Let us prepare a solution of sodium hydroxide NaOH in water by placing 8 grams of sodium hydroxide in the volumetric flask and adding water to produce 250 centimeter cube of solution after stirring. Define concentration in words. What is concentration? Another definition that you should not lose there. So how do we define that? It's the amount, say hambile again. What is it? The amount of solute per dm cube of solution. Yeah. The amount of solute per cubic decimeter of solution. Something like that. Something of that nature. Abanye bathi per liter, right? Calculate the concentration of the sodium hydroxide solution. We have 8 grams, we have 250 centimeter cube. Now, there are two schools of thoughts here. The ones that will go with the formula, C is equals to M over MV, which is straightforward. You are given your mass is 8 grams. And then you're going to say this is for sodium hydroxide. So what is molar mass of sodium hydroxide? We have 23 plus 1 plus 16, right? Which will give us what? 40 grams per mole. Then we're going to put the 40 here. Then there is volume, which is 250 centimeter cube, divide by 1,000, so that it goes to cubic decimeters, and then it's 0.25. Straightforward, you get your concentration, it's what? 0.8 mole per dm cube. Or there will be those that prefer to first calculate the number of moles and then the concentration. So if in nalapho you are not wrong, 8 divided by 40, you're going to get 0.2 mole. And then from there on, you're going to say C is equals to N over V. 0.2 divided by the 0.25, you still land at 0.8 mole per dm cube. Right. So whether you go with option 2 or straightforwardly option 1, it's up to you. And then sodium azide, Na-N3, is used in car airbags for the airbag to inflate. The following reaction must take place. They say calculate the volume of nitrogen gas that would be produced at STP. At STP. So something must ring in our mind here. When they mention STP, N is equals to V over Vm, where our Vm is 22.4 dm cube. So we always know that if 55 grams of sodium azide reacts completely, so sodium azide is this. If this reacts completely, meaning that's the only one, that's the limiting reagent, right? then izothini. So we should follow our stoichiometric steps here, which if I have to remind you of that, we know our stoichiometric steps is number 1, calculate the number of moles. Calculate the number of moles. That's step number 1. Then sodium azide weight to about 55 grams. So N is equals to mass over the molar mass. We put the 55. Then we want the molar mass of sodium azide. Sodium is 23. Nitrogen is 14, but then there's 3 of the nitrogens there. Remember, this 2 is not involved when you calculate the molar mass. Do not make the mistake of putting loyo 2 loyo. Loyo 2 loyo, we're balancing the equation in kuphela. Asimfake will calculate molar mass. Then 65 grams per mole. Now, this is going to be what? That divided by what? By 65. Then 55 over 65 is 0.846 mole, okay? Let me just keep it to 3 decimal places. And then step number 2, what do we want? Calculate the volume of gas N2. So number 2, compare molar ratio. Compare molar ratio. Sodium azide to what? To N2. The ratio is what? 2 is to 3. The way sesikhulume ngakhona nge-stoichiometry, guys, you can't afford to disappoint me. Then 3, this will be 2x. 2x 3 multiplied by 0.846, then divide both sides by 2. Therefore, our x becomes what? 3 times 0.846 over 2, which becomes 1.269 mole. But then what do we want? We want the volume of nitrogen gas that will be produced at STP. So step number 3, calculate for the required value. So you see, that's when I am interested in reading the question when I get to step number 3. Calculate for the required value. So N is equals to V over Vm. 1.269 is equals to V over 22,4. Then when you cross multiply that, you get 28.43 cubic decimeters. Hayibo guys. Injalo. Skatlofe inta bana, skatlofe inta. Tshwarang ntho e. Yo ngola busane. Le passeng. Calculate the number of moles, compare the molar ratio, calculate for the required value. Those are the 3 stoichiometric steps. Hey. Screenshot fast. And then, okay, the last kick of a dying horse now. If a solution of silver nitrate HANO3 is mixed with solution of potassium chloride KCl, a precipitate of AgCl is produced according to the following reaction. A 55 centimeter cube of a potassium a chloride solution with concentration of, so let's see. So where exam uyenza kanje, make sure that you highlight info yakho. Is added to 70 centimeter cube of silver nitrate. Silver nitrate is this, of concentration 0.1 mole. What is meant by limiting reagent? This is the substance that is completely used up in a chemical reaction. The substance that is completely used up in a chemical reaction. Determine which substance is the limiting reagent. We already know how the drill goes here. Which substance is the limiting reagent? How will we determine that? We're going to determine which one is the limiting reagent simply by doing this, calculating the number of moles of both here. So we have potassium chloride, which is the volume is 55 centimeter cube. Then the concentration is what? 0.25. So C is equals to N over V. Concentration 0.25, and then N, volume 55 divided by 1,000. 0.055. Cross multiply this. We have as 0.01375. And then we can go to AgNO3. C is equals to N over V. What do we have? Our concentration is 0.15 mole. Our volume is 70 centimeter cube. 0.15 and volume 70 divided by 1,000, 0.07. Cross multiply here, 0.15 times 0.07. 0.0105 mole. And then now, what's the next step? This is the step that you normally make mistakes on. Remember I said, use the second one as the what? As the reference. And then this is what you do. You will say, let me compare the ratio of KCl to AgNO3. Then you're going to say the ratio is 1:1. If you use this one as the reference, that means sizofaka for this one and say 0.01375. And then we put X on this one, meaning that whatever that I calculate here must then compare to this one. Remember, these are the available number of moles. So let me just write it on the one we reference. So these are the available number of moles. And then I want to calculate here when I cross multiply 0.01375 mole. Right? Now I want to compare these two numbers here. Between this number and that number, which one is bigger? Now it's a bit challenging. So you have to follow and say, okay, kuno 0 la, kuno 0. Kuno 1 la, kuno 1 la. Kuno 3 la, kuno 0 la. So meaning this one is bigger. This one is bigger. And this is the one that is required. This is the one that is required. Now we have this available, but we require this. So which means that our conclusion is in, if the number of moles available are greater than the number of moles required, then substance is in excess. But if the number of moles available are actually lower than the number of moles required, then substance is the limiting reagent. Once ukwazi ukubamba lama conclusion, ucompare ngala ufake khona u-x, ucompare ngale nto le, ngalama number of moles wale ozobe ufake u-x phansi kwayo. So I can't take this number and compare it to that one. I must take this number and compare it to this one, which is 11. Now I can see that the required is bigger than the what? Than the available, or the available is smaller than the required. Therefore, my conclusion is what? AgNO3 is the limiting reagent. Is the limiting reagent. It's like that. It's like that. So don't confuse step number 2. A lot of people, they get confused when they get here. Make sure that you know what you are doing here. With calculating the number of moles for both, yes, but now when it comes to making one of that the reference, you must know what you apply. If I had put X here, show it being so being my number of moles wale. Right? Let's say now I had decided to do this. Hope you are done here. Let's say I had decided to say KCl and then AgNO3. So 1 is to 1. Then kube ngifake X la. Then kusho ukuthi la bengizomele ngithi 0,0105 and then cross multiply. Then 0,0105 mole. But then I'm going to compare this number to which one? To KCl. No. I'm going to say this number I compare kanjani ngale. So this would be the available and this would be the required. Now, if I check this, I would see with what I have available is actually greater than what is required. Then my conclusion would be that KCl is in excess. If KCl is in excess, therefore it means again AgNO3 is the limiting reagent. I will change. The fact that you now make the other one the reference will not change their answer. Because in this case, you'd be proving with KCl in excess. Now we know that if one is in excess, the other one has to be limiting. Inshallah. Now, there was this one question in particular that I saw that had a graph like this. I want to talk about it. And then you were given 20, no 12,7 lab. Now, you should still do the same thing lapho calculating the number of moles and what so not. But then here, i-mass exomedwe seventies. It's not the 20, it's not the 12.7. This is the mass that would have reacted. So if you want to calculate the number of moles available, then kuzomele uqale ngalowo mass leyo uthi okay, to calculate my mass now would have to be 20 gram minus 12.7 gram, right? Then from lapho ke, you will get 20 minus 12.7, and then it's 7.3 gram. This is the one that you'll be using to calculate my number of moles. You'll be using this mass and saying N is equals to mass of the molar mass. You calculate my number of moles using this, not using 20, not using 12.7. So ngiyazi ukuthi bakhona banalo lelo phepha, niyazi ukuthi ngikhuluma ngani. Okay, yes, this is the last question. Then, so we have determined which substance is the limiting reagent. What mass of AgCl has precipitated? So we are looking for the mass of this one. Then, sizotini, we will have to use, now when we compare, we have to compare based on the limiting reagent. So this is the limiting reagent and this is the available number of moles of the limiting reagent. So sizoti AgNO3 to AgCl. Again, the ratio is what? 1:1. But for those number of moles, we have what? It's a 0, 0,105. Okay. 0,0105. Yeah. So AgNO3, 2Ag, and then Cl. 1:1. 0,0105. That means now is 0,0105. So to then find the mass, we will use that number of moles. So 1 mark for this. And then mass of AgCl will now be what? The number of moles multiplied by the molar mass. 0,0105 multiplied by molar mass of AgCl. What is Ag from the periodic table? Ag, silver, 108. So it's 108 plus 35.5. 108 plus 35.5 is 143.5 grams per mole. Right? Then 143.5 times 0.0105. Then we have 1.51 grams. That's the mass that precipitated. Yep. And then Mary hits 50 grams of calcium carbonate that reacts according to the following reaction. Determine the number of moles of the calcium carbonate. Straightforward. Mass over the molar mass. So we have 50 grams. We already know calcium carbonate is 100. 0,5 mole. So formula, substitution, correct answer. She obtains only 18.2 gram carbon dioxide gas. Determine the percentage purity of the calcium carbonate. Okay, the percentage purity. So now that means to calculate the percentage purity, we have to compare it with that, right? And then let's say carbon dioxide. So first, step number 1, percentage purity. Calculate the number of moles. Remember, we know with percentage purity, we can either work with the limiting reagent, or if the limiting reagent is not provided, we work with the product. In this case, we are working with the product. Calculate the number of moles of the product. And as a spawning by the carbon dioxide, even in that question we were doing, I think it was the same thing. So you see, ayafana lama question, guys. Yes, it was the same thing. We had to calculate the mass of carbon dioxide. We had to calculate the mass of carbon dioxide. Then in order to find the percentage purity there. So it's the same question repeating itself. And then what do? We are given 18.2. So number of moles, mass over the molar mass. Remember, we are calculating for carbon dioxide. It got 18.2 divided by what? 44, right? So that's 12 plus 16 times 2, yes. And then 18.2 divided by 44, that's going to be 0.4136 mole. And then second step is to do what? Second step is to compare the molar ratio. Stoichiometric steps that we are following. So carbon dioxide to calcium carbonate. it's going to be what? So it's balanced, right? Yeah. So 1:1. 0.4136, that means now 0.4136. Then now we have to calculate the mass of the pure calcium carbonate. So to calculate the mass of calcium carbonate pure, it's the number of moles multiplied by the molar mass. 0.4136 multiplied by 100. 0.4136 multiplied by 100. That's 41.36 grams. And then step number 4, that's percentage purity now. Mass of pure over the mass of the impure times 100. Then the 50 gram, we know that's the one on the freezer now, right? So this is the impure. So we're gonna say 41.36 divided by 50 multiplied by 100. What is the percentage purity? 41.36 divided by 50 times 100. It's 82.72%. Yebo. Then that's basically that. So you follow those 4 steps when it comes to calculating the percentage purity. It's still the 3 stoichiometric steps with the addition of this one. And then I confuse in about theoretical yield and the percentage yield. Percentage yield has its own formula. Percentage yield says actual yield over theoretical yield times 100. In that case, you are mostly given the actual yield and then you have to calculate for the theoretical yield. Here, you are given the impure, you have to calculate the pure. So kulena unikwa i-numerator ufuna i-denominator. Kulena unikwa i-denominator ufuna i-numerator. So know the difference. Yeah. Final boss. Calculate the mass of carbon dioxide gas that Mary could collect if calcium carbonate was only 70% pure. So if it was 70% pure, that means this is a reverse calculation now. This is a reverse calculation. How do you perform those calculations? You're going to do it in reverse. Percentage purity is mass of pure, so we're going to start here over mass of impure times 100. Now remember, if the purity changes, it doesn't mean the impure has changed. The impure will still stay the same. It's 50 gram. That means it's the pure substance that actually changed. So we have what here? 70%, which is just 70. And then we no longer know the mass of the pure, but then the impure is still layer of 50 times 100. We want to cross multiply this. So this is how you do it. Total of 50 multiply with 70. Total of 100 to multiply with x. Right? So 70 times 50, that's 3,500 is equals to 100x. Divide both sides by 100. And then x wakho kuba ubani? 35 gram. So that means if it's 70% pure, that means there's only 35 gram that is pure substance. Now that 35 gram also calculate a number of moles of the pure. So everything that we have done, we are now doing it in reverse. So to calculate the number of moles of the pure now, number of moles of calcium carbonate pure, you're going to take that mass multiply it by the molar mass. So 35 multiply it by molar mass is what? 100. Oh, what am I doing? Number of moles is equals to mass over the molar mass. 35 divided by, then 35 divided by 100, it's going to be what? 0.35 mole. Yes. Now you want to compare the molar ratios. So everything that we did in reverse, carbon dioxide, the ratio is bunny, still 1:1. So this is 0.35. That also needs to be 0.35. And then now to calculate the number of moles of carbon dioxide, I mean the mass of carbon dioxide, number of moles multiplied by the molar mass, 0.35 times. So when we say we are doing in reverse, that means labo divide corner, so we are multiply. Labo multiply corner, so we are divide. Then this is 44. 0.35 multiplied by 44, 15 comma. So the mass will be 15.4 gram. Now so that's what we call a reverse calculation. Okay, guys, yes, and that's it, we have killed another 3 hour, 30 minutes again. So yeah, I've went through everything. Obviously, I just took out the multiple choice. Ngizoshaya umagogo style lapho nivala amehlo nibuka ukuthi isandla siwelaphi. So yeah, that is it, guys. That is it. Make sure with the time that you have remaining, go through everything. Now, Bonile, as we were going through, I'm sure you picked up with, okay, this is where I need to revise. This is where I am actually lacking. So please make sure ukuthi uyahlala kulawo topic that you feel like you will be losing marks, and make sure ukuthi you strengthen that. Awusanayo enye chance. You only have this final exam. So asifuni sikhale next year. Everyone that I'm tutoring, I have hope that you will pass. I have hope that you will all pass. No one will come with bad results. So, okay, guys, right. We are fine then. Good luck, all the best on your paper. Make sure that you nail it. Keep out everything that you got, right? Give it your all. Otherwise, good night. Bye. It's a chai from me.
Hi, see Machita.
Injalo,
Bye
injalo.
bye.
Wee.